Hi everyone, this is Yawen Wang from Stanford University. Today I'll present our work on SmartHarvest, harvesting idle CPUs safely and efficiently in the cloud. This is joint work done in collaboration between Stanford University and Microsoft Research. Cloud computing has emerged as the dominant platform for computing in recent years. However, despite its growing popularity, the underlying resources in the cloud are not always getting effectively utilized. This figure is taken from Resource Central, a paper published by Microsoft in 2017. It monitored all the VMs running on Azure for a 3-month period and reported that 60% of those VMs have an average CPU utilization of below 20%. The common reason for CPU underutilization in the cloud is that users often over-provision their VMs based on the peak load, and this is especially true for user-facing workloads that require consistent low latency. One common way to improve CPU utilization in the cloud is to use spare resources from latency-sensitive workloads to run batch processing tasks. In order to do this safely without violating performance constraints of latency-sensitive workloads, prior works have either required extensive offline profiling or knowing application-level performance metrics or characteristics. Unfortunately, these prior approaches are not applicable in the public cloud. And this is because VMs are often opaque boxes in public cloud. Cloud providers have no knowledge of what is running inside the VM. Therefore, in public cloud, we can only monitor VMs with low-level counters, such as their CPU usage. And to be more careful when borrowing cores from VMs, we should be conservative and assume that any VM may be running latency-sensitive workload. We're proposing a new solution called SmartHarvest to improve CPU utilization in the cloud. It uses online learning to continuously learn and predict future CPU utilization of opaque box primary customer VMs based on their past usage. It safely harvests unused cores from primary VMs to run low-priority batch processing jobs inside a new type of VM called Elastic VM. It uses a 2-level safeguard design to help reduce performance impact on primary VMs when the learning model frequently underpredicts their CPU demand. At runtime, SmartHarvest dynamically allocates cores among VMs to achieve 2 goals. First, minimizing impact on primary VMs. For example, we show in our evaluation that SmartHarvest incurs less than 10% performance impact on primary VMs. And secondly, maximizing the number of spare cores getting harvested. I'll next describe Elastic VM, a new type of VM that we're introducing. Elastic VM runs batch workloads on idle cores unused by primary VMs. It has a minimum set of guaranteed resources. These values are tunable. In SmartHarvest, we allocate 1 physical core, 8 GB memory, and 10 GB SSD to the Elastic VM. It will not be launched if there's not enough resources on the server to meet this minimum. It has lower priority than primary customer VMs, and the number of cores assigned to it will change dynamically based on CPU usage from primary VMs. Lastly, it's configured to have as many virtual cores as the total number of physical cores on the server, so it can always make effective use of any harvested cores. Let's now go over the high-level design of SmartHarvest to see how it works. In this diagram, the orange box shows a 10-core primary VM that is currently using 5 out of its 10 allocated cores. The green box shows the Elastic VM, which starts with a single core. The gray box shows the mean root partition of Hyper-V on the server, where we run the EVM agent. The EVM agent is responsible for monitoring server-wide CPU usage, learning and predicting CPU usage of primary VMs, and also reassigning cores among primary VMs and the Elastic VM. Let's suppose that the EVM agent predicts the primary VM will need a peak of 7 cores for time window TI. Then the agent can shrink the CPU size of primary VM to 7 and reassign the remaining 3 idle cores to the Elastic VM. This leaves primary VM with an idle buffer of 2 cores. The idle buffer can help absorb any burst from primary VM during time window TI. If at the end of TI, we observe the peak CPU usage of primary VM was 6 cores. Then we have provisioned enough cores to observe the CPU peak usage of primary VM. And we now have full feedback for the agent to update the learning model and make a new prediction for the next time window. Based on the predicted peak, the agent can then adjust the VM sizes accordingly. Let's now consider a different situation. Let's suppose the primary VM uses up all its assigned cores during TI. Then we have a safety violation because the primary VM could have needed more cores, hence suffering from performance loss. In this case, we don't know what the true peak usage of the primary VM is, so we only have a partial feedback. Without knowledge of the true peak, we will not be able to update the model. The agent now conservatively estimates primary VM's CPU peak for the next time window to be 1 plus the peak observed over last second, and return cores to the primary VM from the elastic VM. We call these actions as a short-term safeguard in SmartHarvest, and it is triggered when we don't have full feedback information to utilize the learning model. Additionally, the EVM agent monitors the primary VM's vCPU wait time to be dispatched onto physical cores, and we use that as a proxy for VM performance. When the primary VM experiences long vCPU wait time, the agent returns all its cores back. And we call this a long-term safeguard. It is triggered when we infer performance degradation of primary VM from long vCPU wait time. This could happen if the workload run inside primary VM is unlearnable and the agent continuously underpredicts its CPU usage. Next, I will discuss how SmartHarvest predicts VM CPU usage to help safely harvest idle cores. The constantly changing CPU utilization of VMs makes it challenging to accurately predict their future usage. To address this challenge, we use an online learning algorithm in SmartHarvest, which updates the model with each newly observed data point. The online learning approach avoids offline training and profiling, making it possible to learn different workload characteristics after they have started. We also choose to make predictions of CPU usage of primary VMs on a fine time granularity of every 25 milliseconds. This helps the learning model quickly detect changes in CPU usage patterns and adapt to them. The prediction target in SmartHarvest is the peak CPU usage in number of cores of the primary VM for the next 25 milliseconds. The set of features we use include 5 simple statistics: the average, standard deviation, minimum, maximum, and median, computed from past CPU usage data of the primary VM. We considered additional features such as different percentiles in the distribution, but found these 5 features to be the most useful. When deciding what model to use for online learning, we considered 2 requirements. First, we want the model to be simple and lightweight, so it takes less computation resources and can make frequent predictions. This leaves complicated models such as neural network out of consideration. Secondly, we want to be able to differentiate between under and over predictions when updating the model. Under predicting CPU peak of primary VMs is a more severe problem because it can negatively impact primary performance. Thus, under predictions should be treated with higher penalty than over predictions. With these 2 requirements in mind, we decided to use a cost-sensitive multi-class classification model in SmartHarvest. It trains a separate linear regression model for each class. The class with the lowest predicted cost is chosen as the prediction. It allows flexible cost assignment to different class labels, and it also is lightweight and provides fast prediction and update times. I'll now go over the workflow of the learning algorithm with a diagram on the right. First, features are computed from CPU usage data in a time window TI. The features are then passed into the model, which outputs a predicted class representing the predicted peak number of cores that the primary VM will need for the next time window TI plus 1. At the end of TI plus 1, the model is updated based on the actual peak CPU usage of the primary VM from that time window. Once the model is updated, The feature will be computed based on observed CPU data from Ti plus 1 and be used to predict the peak for the next time window, and then the loop just repeats. When we know the true peak CPU usage of primary VM from a time window, we have full feedback to assign a cost to each class label and update the model. This figure shows the example cost function we use to assign cost to class labels for a 6-core primary VM. The cost linearly increases as the class label becomes further away from the true peak. Based on the true peak usage, classes that were under-predicting are penalized more to skew the model away from aggressive harvesting. On the right, it shows the cost assignments for the 6-core primary VM, where the true CPU peak for a given time window is observed to be 3 cores. We can see that classes that would underpredict have significantly higher costs than classes that would overpredict. We also compared this cost function with alternative cost functions that are symmetric or hinged, and we found this skewed cost function achieves the best balance between number of cores harvested and performance impact on primary VMs. We implement the EVM agent as a single-threaded process in the user space. It runs in the root partition of Hyper-V and uses hypercalls to monitor CPU utilization and vCPU wait time. It reassigns physical cores to VMs using the CPU group mechanism provided by Hyper-V. We implement the online learning component using the WAPA-WABIT library, which provides a fast implementation of the cost-sensitive multi-class classification algorithm. Model update takes less than 15 microseconds on average, and the average inference time is less than 10 microseconds. For evaluation, we run 4 different latency-sensitive workloads in the primary VM. We look at their P99 latency to measure the impact of harvesting on their performance. For the elastic VM, we run CPU Bully, a synthetic CPU-bound workload that helps estimate the number of harvested cores, and also 2 real batch processing workloads, HD Insight, which trains a machine learning model with TensorFlow and TerraSort. We compare SmartHarvest with 2 alternative harvesting policies. The fixed buffer policy dynamically adjusts primary VM CPU size to ensure there's always a fixed number of cores in the idle buffer. The previous peak policy simply estimates peak CPU usage of the primary VM based on the recent peak observed over last 25 milliseconds. We conducted our experiments on a 2-socket Intel server with 24 cores per socket. Let's first look at some CPU usage data of the 4 primary workloads. We run each of them for a minute inside a 10-core VM. The first row in this table shows the average number of cores used by each workload. The second row shows the average of the peak CPU usages, where each peak is computed over a 25 millisecond time window. The large difference between the average usage and their peaks indicates that these workloads have bursty CPU usage patterns. Let's now look at some results when we co-locate a single primary VM with an elastic VM. For each experiment, we run a different latency-sensitive workload in the primary VM and CPU bully inside the elastic VM. This set of figures show that the baseline P99 latency for each primary workload when no core is getting harvested. The horizontal line marks a 10% increase from the baseline P99 latency. Let's first look at the performance of different fixed buffer policy. Each data point is denoted with a corresponding fixed buffer size next to it. The general trend for the fixed buffer policy can be observed across workloads. As we increase the size of the fixed buffer, the impact on the P99 latency decreases, but it also harvests fewer cores. When we pick a single best fixed buffer size that harvests the most while staying below the 10% increase, it is different for each workload. This is expected as each workload exhibits a different CPU usage pattern. For the previous peak policy, we noticed that it can significantly increase the P99 latency for some workloads. This is due to sudden increases in CPU utilization that is not captured from the recent peak usage. Finally, let's look at the results for SmartHarvest. Online learning allows SmartHarvest to learn different CPU usage patterns at runtime and make predictions about their future CPU usage. With the predictive power of SmartHarvest, it consistently harvests 1.5 to 3.5 cores across different workloads without per application tuning or any application level information. At the same time, SmartHarvest also has less than 10% impact on P99 latency for all workloads. When we look at all the results side by side, we can see that SmartHarvest outperforms alternative policies by harvesting a good amount of idle CPU resources while maintaining a small impact on different latency-sensitive workloads. We next run realistic batch processing workloads in Elastic VM to confirm useful work can be done using harvested cores. These two figures show running IndexServe in the primary VM and TerraSort or HD Insight in the Elastic VM. We can see that both of the batch processing workloads can achieve more than half of execution time reduction using the cores harvested from IndexServe. These results show that SmartHarvest is robust to different batch workloads run inside Elastic VM. When harvesting from multiple primary VMs, we treat multiple VMs as a single entity and predict their aggregate CPU usage with a single machine learning model. These two figures show two primary VMs, each running memcached, and CPU bully is run inside the Elastic VM. The results are shown with varying fixed buffer policies. Now, in order to not increase the P99 latency by more than 10% for both primary VMs, for the fixed buffer policy, we need a minimum fixed buffer size of 17, even though a fixed buffer size of 7 was enough to stay below the 10% line for a single memcached primary VM. This is an indication that the aggregate CPU usage of two memcached VMs are much more variable. With SmartHarvest, it is able to successfully harvest two cores while maintaining small impact for both primary VMs. However, if we did not have the long-term safeguard in SmartHarvest, which is a case illustrated with the yellow triangles in these figures, the P99 latency could get more than 50% worse. This is because the aggregate CPU usage from two memcached VMs have more variations, making it more unpredictable. The long-term safeguard helps detect such workloads that are challenging to predict for and stop harvesting to protect their performance. We have completed a more thorough evaluation of SmartHarvest, including comparison of different learning window sizes, cost functions, and safeguard designs. We also explored the trade-off between system responsiveness and the benefit of learning by implementing a faster mechanism to reassign CPU cores. Due to the limited time, these additional results are not covered in this talk, but we invite you to read about them in our paper. In conclusion, we have designed SmartHarvest to manage cloud CPU resources with online learning. It automatically learns and adapts to CPU usage of different applications and varying load patterns inside opaque primary VMs. It harvests spare CPU cores while minimizing performance impacts on primary VMs. And the evaluation results show that it can effectively improve CPU utilization in the cloud. Thank you, and you can contact me via email for any questions.